Hi, for those who've been watching for a long time, and I mean like more than a decade, you might remember EEVblog number 50. Well, you won't remember the actual number, but you might remember the CREE LED thermal design video, which was, well, only gotten 50,000 views over like the last 11 years or whatever, so not that impressive, but I think it's a really good video going into thermal heatsink design, and I actually used a clip of that in my my 10-year-old intro video, which I have to update. Anyway, those who remember that video might remember these homemade, obviously, CREE LED strips that I made. I know they look crusty now, but they looked shiny as almost like 11 years ago now, and these are for my outdoor deck. And you know, LED lighting wasn't like as ubiquitous then as it is now, and really, you know, you couldn't buy like the LED strips and things like you can these days, so I made up my own using CREE, what were state-of-the-art at the time, CREE XPG LEDs here, and I stuck them down into a big aluminium plate here, none of that aluminum rubbish, and with some thermal adhesive here to act as a gigantic heatsink. And I did lots of whiteboard calculations and all sorts of stuff about, you know, generic thermal design. So the video was more about that than it was about installing these LEDs. But anyway, these have been up on my back deck. They were like up on beams on my back deck, then shining upwards from the beam and then rebounding off the white roof and then, you know, coming down. It was designed to look all funky, and it did. It was really quite nice, and I've had and the reason that I put them on really thin strips like this is so that you couldn't, from the ground, you couldn't see them. The lights just magically turned on, ta-da, and like as if they're coming out of the beams or something like that. So yeah, and they've been in there for 11 years. I just took them out, and I noticed that like a couple of years ago, like some LEDs started to fail. So they lasted probably about 7-8 years, something like that, like fully exposed like this. I did not coat these in anything. I just soldered them on, put the thermal adhesive down. I just used some, I think I tacked, did I tack these down or something? Maybe with some hot snot or something. But anyway, so they have been sitting out, and not in the weather, of course. They've been under a, like a back deck pergola thing. But anyway, they're still crusty. I've cleaned them up a little bit, but yeah, as you can see, there's a lot of crust, pretty crusty burger on there, and let me get you a close-up shot of one of the LEDs. There we go, that's what one of them looks close up, and yeah, it leaves a bit to be desired, doesn't it? That's what weathering does to, yeah, poor old unprotected, you know, I should have like maybe, you know, silicon gunked up the whole thing or something like that. But anyway, they did last quite a long time, and as I said, a couple of them have started to fail. Now, because these are all 8 LEDs in one big series string, and I drive them with a 700 milliamp constant current driver with a compliance voltage of, I think it's about 40 volts. It's up in the roof somewhere. Haven't double checked that, but anyway, like a high compliance voltage, 700 milliamp constant current driver, but these things still work, but a couple of LEDs have failed. So I'm going to measure these. I presume like they must have failed short circuit, because really that's the only way that the LED strip can actually keep going, of course, because if one of them fails open circuit, then the entire string is just gone. And they were both working fine, and it's sort of like after the first one failed, like 6 months later, like another one failed, and then eventually another one. I think we only had like 2 or 3 LEDs on each strip left, and, you know, Mrs. EEVblog went, fix it. So here we are. And they eventually just stopped working. So I presume like one of them went open. So I expect to find like a few shorted ones on here, and eventually like one open, or maybe like a busted solder joint or something like that perhaps. So let me get my 15 volt diode mode here. I don't need that, but it's just nice. It pumps a bit more, allows us to put a bit more current through. What's that? The negative one is here. So let's, yeah, that one works. That one works. That one works. Yep. Oh, that one's a short. We can get in there with the meter, and that one's working. Another one on that same strip, so two working and 2 failed on that strip. This strip's better. Yeah, that one's open. And that one's shorted, our first shorted one on that strip. Shorted. shorted. There's lots of shorted ones, so it'll be interesting to see, like why I presume that they're shorted on the die. I mean, you know, it's not like it's not like all the crusty dirt and stuff is going to cause a short on there. Wow, yeah. Yeah, I can remember quite a few of them being out, and this one just completely came off here. So that's no good. Oh, yeah, it's not even, nah. Oh, there's nothing left. And winner chicken dinner on the last one. So how shorted are we talking here? Well, look at that, 0.16 ohms. And just for completeness, I'll reverse that. But I think you'll find that, yep, 0.17, that's like shorted. That's got to be like a short on the lead. Look, I know it looks really crusty in there, but oh geez, you know, you wouldn't expect that from dirt. Don't actually have my cleaning brushes moved over to the lab yet. I've got none of my cleaning stuff moved over, and I'm still measuring, yeah, a dead short on there. I think it's Gonski inside the lead itself. Now, of course, I don't think it's really worth like actually repairing these, because then I'd have to scrape off all the thermal adhesive and then like sand it all down and glue it all back on, and I'd have to order more thermal adhesive and like rewire it back up, clean the whole thing back up. I don't think it's worth the effort. But I do have plenty of these T8 LED lights here, diffuse type, and ones that had just a clear thing on the top, like old lab lighting, and I thought I would just maybe just repurpose these things, crack them open and have a look, because it's actually, I've been looking around and it's not that easy to find exactly like I've got here, which is like one string. Like I've got 8 LEDs on here, okay, and you know, roughly like maybe let's just say like at most like 3 volts drop per LED, only talking like, you know, a 28 volt drop. So like maybe we could have like if you had like less of a drop, you could have like, you know, 15 LEDs in a single string for like driving with like a 40 volt compliance voltage, something like that. And they're actually really hard to find. You can find like tons of them with lots of LEDs like this, and we'll have a look at the configuration in a minute. But of course, these aren't all going to be in series, because then the voltage drop would be too much. You'd need like hundreds of volts compliance voltage, and well, that's just not how they work. So obviously they're going to have like multiple strings, and they're just going to parallel them up, and they're just relying on the dynamic resistance of the diodes to try and balance the current between the different strings. That's my guess anyway, because this one, as we'll see close up in a minute, this one doesn't have any LED droppers at all. So these are current driven LEDs and not you know, not like a voltage output of the DC to DC converter and then just driving with a, you know, a dropper resistor, as like a lot of your cheap little, you know, you can buy all these tons of different types of LED, like decorative type lights on you know, reels and things. You can get like, you know, 10-meter reels for cheap of these things, but that's not what I want. I want really like high brightness output, preferably just one string, like, you know, 10, 15 LEDs tops in series. And I really couldn't, I had a hard time finding something like that off the shelf. So I thought, oh, well, I've got these, might as well repurpose them. I've got no other use for them. So let's have a look. I've already cracked this one open. Let's crack this one and see what's inside as well. So this one here with the aluminium backing on it, just a you know, one hung low brand T8 tube, although it does have a part number, so you can look that up. 18 watts, nominal 5000K. I've measured them, they're not 5000K. Be careful, be very careful with LED lights. I'm pretty sure I've done like a second channel video on this. Yeah, you can really come a gutser if you, or you know, don't get them from a reputable manufacturer. You'll find that, you know, I think these ones measure like 6,000 or over 6,000 or something. It's just absolutely nuts. Anyway, very nice aluminium extrusion, and they've got the DC to DC converter in there. I can't pull that out, so obviously they solder in these wires as a last step, so I've got to unsolder those to pull that out, but I might actually measure that. So just for fun, I thought I might actually just measure that first. That's nice and big enough. I can get my new clamp probe, oscilloscope clamp probe, which you can get on the EEVblog store now, by the way. I'm stocking that, haven't done a review or teardown of it yet, but it's a, yeah, well, I have torn down, and it's really, well, I've posted photos on the EEVblog forum. Anyway, very nice bit of kit. So I might just, yeah, measure, just for kicks, measure the, but this is going to be constant current, because as you can see there, they're using they've got the aluminium PCB directly slid into a channel on this aluminium extruded housing, and they're using it as a gigantic heatsink, and it's a very nice design. I like this. And the thing about this is, watch it, watch it, watch it, watch it. It's still, hopefully this stays in focus. There's no joins in this PCB. This is a 1.2 meter, because these are nominal 1.2 meters, so just under 1.2 meter long PCB, and that would have required a pretty specific manufacturer to actually not only make the bare board, because that's bigger than your regular panels, but also to assemble as well. And I can't see this on the camcorder LCD, so hopefully if I get it at the right angle, otherwise you're going to have to trust me. So there's no room for surface mount LEDs on here. There's none on the bottom. There's none on the top. They can't put them all in a series string. And if you have a look carefully, you'll find that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in series before there's one strip all the way along here. So there's one strip like this. Boom, goes up to here. Series, 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 and then goes up to positive. There's another positive strip along here. And then it starts another. So they've got parallel strings of 12 LEDs all in parallel, and there's no current sharing resistors, so this will be a constant current drive. They're not going to use constant voltage, that'd be silly. They're going to use constant current drive, and then they're just, as I said, going to use like the dynamic resistance of these LEDs to try and hold your tongue at the right angle, cross your fingers, and hope that the current is shared fairly equally between all the LED strings in parallel. Not best practice, by the way. Don't recommend it, but, you know, you can get away with it. And the other one I got here is actually branded. I believe this is German, Muller Light. TO, once again, 18 watt. These are 4000 K, so lower color temperature. I use 5000 K for everything in lab here. There you go. 97 milliamps, 1700 lumens. Well, that's from the AC, of course. That's not what the LEDs are actually being driven at. And they've got a converter up this end and converter up this end as well. So I don't know what the story is there, because there's only contacts at one end, because one end is just nothing. It's just a shorting link in there like that, and exactly the same on the other one. It's just a shorting link, and the other end is actually wired up with the pins. So, you can see the extruded aluminium backing down in there, and this sucker ain't coming out, so yeah, I might have to slice open the plastic. I don't know how to get these damn things together. I thought I wasn't going to go far in this one, but unfortunately I had to go like a third of the way along here before I finally found the point. That's it there. So, count up those, 24 LEDs in series for one string. So, that's impressive. So, a reasonably high compliance voltage from this puppy. Once again, must be constant current. There's nothing in it. Couple of chokes. Cap across the mains input. We've got diodes. Where's the constant current controller? Geez, I'd settle for like a single transistor constant current generator, but we got nothing. It looks like just a full wave bridge rectifier. Hang on, I managed to bash this open, and I think our constant current generator's up this end. That's got to be the trick. Hopefully I can slide this through. Yep. Ta-da! There you go. That's the trick. Yes. It looks like we've got our constant current generator down this end, because it just didn't make sense the other end. We have a look at what's under there. Aha, there it is. That's actually an SSL, not an SL, SSL 2109, and I'll whack up the data sheet for this, and this is, yes, it's a like high voltage LED driver, so it's designed for direct mains conversion, which is what we see up the other end. It's just interesting that they whack it all in, like they separate it into two ends, which means you have to run the high voltage right along the PCB down to here for the driver. So anyway, that is not an isolation transformer. That would be the inductor required for this thing. And then over there, looks like that's probably our switching transistor. That's our external switching transistor. There must be a diode in there somewhere. Yep, I can see that under the cap there. And it's almost certainly like straight out of the application note. So here's the application note circuit for that thing, and you can see that, yeah, it's basically high voltage mains rectification, so high voltage DC, and then it just does its buck constant current business. There's a current sense resistor in there, and as we saw in the other one, we're going to have multiple strings in parallel because it's still, even with that high voltage, doesn't have the compliance voltage for all of these LEDs in series. So, and as we saw before, 24 LEDs in series, and I measured them with my meter just at, you know, a few milliamps. It was about 2.7 volt drop, so we're talking about, you know, a 64 volt compliance voltage for that string. So yeah, it's reasonably high. And aha, there it is. We've got a 100 volt cap there. So yeah, obviously the compliance voltage is under 100 volts. You know, it's probably in the order of like 70 volts, something like that. So if you can see on this board, this is why we actually have 3 connections and 3 traces. This positive here, this is the 240 volt mains rectified, going straight down here like this, and then the other side over here is ground that goes all the way back. That's not connected to anything. And then of course you got a third one in here, which is your LED strings. Hopefully you can see that. If I get it at the right light at the right angle, you can see. Yeah, I think you can see that. Yeah, and then that runs off to, once again, once it gets to the 24th LED over here, bingo, that's 24 in series, and then it'll have another 24 in series, then another, and another. So I'll have 4 strings of 24 in parallel. So as it turns out, this one has too high a voltage compliance requirement for my existing supply that I've already got in place, and it's difficult to get at in the roof. I've got to take the tiles off the roof, and it's really ugly. I remember installing the damn thing, and it was a nightmare, and I don't want to go up there and change it because all the wiring's in place and everything's hunky-dory. So I just want a LED strip that I can plug into the existing wiring to replace my crusty old ones up here. So I could possibly repurpose this, although having that shape, it's not exactly going to just sit there on its own. You might be able to see it, and B, it might rock around like that. Might have to, I don't know, elastic it down or do, I don't know how I'd stick that down, but onto a wooden beam, it's not nice. I could probably, like, you know, cut it off because I don't need the whole thing as a heatsink, I doubt. I could probably get away by chopping off the curved bottom of it, but I don't know. Anyway, this one would work. If I just go whack that in, I believe it should current balance okay with the parallel strings, and it should just work a treat. Alright, so what I'm going to do is I'm actually going to power this strip up, measure the current. So I'm using my new Mixig CP2100B. Disclaimer, I now sell this on the EEVblog store because it's excellent, and yes, I do plan, once the lab is back up and running and I've got some time, do plan on doing a full review for this thing. But those supporters and those on my email list did actually get a bargain on this on the first stock, but I still have them in stock, so it's like the best value. 2 megahertz bandwidth, and it's yeah, it's pretty cool. Anyway, I won't go into all the details. You can check it out on the EEVblog forum. People have been like comparing it and stuff with other units on the market, and it pretty much blows them all away. So that's why I'm carrying it. Anyway, let's power this thing up. I've got it set. I'm using the 10 amp current range, so we'll get 0.1 volts per amp out. So I've set up my scope for 200 milliamps per division, so it's set up, if you want to go in and check it out, probe, there it is, amps and 0.1 volts per amp division. So let's power it up, and well, there we go. Let me trigger on that bad boy, and she's got a bit of ripple on there, doesn't she? So we've got our AC RMS down there. What we want is our DC RMS. We'll just take our full screen, that's fine. Won't worry about the end cycles. DC RMS, 420 odd milliamps. So there you go. I've got a 700 milliamp driver, so yeah. Just for kicks, let's see what happens when we drop the voltage on this thing. These are worth their weight in gold, these variable frequency converters. So I was running that at 220. So keep going. Should be universal, so should do fine with the Yankee voltage. But, oh, it's doing pretty well. Come on. Wait, oh, look, look. I created a flasher, a LED flasher. 555 timer, eat your heart out. Look at that. That's fantastic. So, yep, it's hiccuping. It's the technical, you know, repair term, like troubleshooting term. Power supply is hiccuping, and yep, that's great. And yes, it even down at 100 volts, it's still a constant current, you know, 430 milliamps. So yeah, definitely constant current driver. I'm pretty sure I've got a 700 milliamp driver on mine. I'll have to test that before I install it because, well, the thermals may not be adequate for, you know, overdriving it at 700 milliamps. I mean, I could whack it in until it fails, I guess. I don't know. It's going to burn my pergola down. Hope not. Wow, that converter's a lot longer than I thought it would be. I pictured something like, you know, this long. Let's crack it open. Well, that looks surprisingly nice. Like I thought these were, well, you know, they haven't exactly got Panasonics in them. They got Samsung caps in them. But, you know, it actually looks like a decent design and build quality. They haven't tried to, like, skimp and make it really small. Yeah, the TO20's flapping around in the breeze there, but no biggie. Because, you know, it's not like these are in, like, high vibration environments or anything like that. But that looks really well designed. All the input protection. Is that an input fuse there? Quite possibly. I really like that. It's all single-sided construction, of course, to get the low-profile form factor, the height. They've had to do some cutouts in the PCB here. Very common for the transformer and even the large caps here on the end. But on that double-sided surface mount rubbish, that looks really groovy. And that's a BP3309 driver IC for those playing along at home. Here's a quick look at the datasheet. But yeah, apart from that, of course, you know, mains input. Yeah, we've got input choke, very nice. The mains input filter caps, and then full wave bridge rectifier. Of course, just generating the high voltage rail, and then just like, you know, switching external switching transistor, and then we're implementing a what looks like an isolated driver here. So that's pretty sweet. Has that got secondary side regulation? I don't think it does. I'm not seeing any controller on the secondary side and no feedback really. So yeah, it's primary side regulation, which is a bit how you're doing, but you know, it does the business. Well, I'm now driving this with a 1 milliamp constant current load, and as you can see there, current sharing absolutely perfectly, like even down to a milliamp. All those parallel strings, no problem whatsoever. So, show you, oh, so it's 2 milliamps, what are we, 10 milliamps, 50 milliamps, and so forth. 300, so that's 460, so that's kind of where we're running before. So it'll do 700. So there's our 700, and you can see that it's dropping 40 volts. So it's just so it's 700 milliamps. I believe the compliance voltage of my driver is well, there we go, is 40 volts, 700 milliamps. Of course, this is constant current. When I'm talking compliance voltage, I mean that the string will take as much voltage as it needs, but the compliance voltage is the maximum voltage that the supply can supply. You can use your power supply as a constant current LED supplier by setting a constant current and setting the maximum compliance voltage. In this case, I'm using channel 3, which goes up to 0 to 64 volts. So I've got up to 64 volts compliant voltage, but I can change that just by setting my maximum voltage. You can see that my maximum voltage there is set to 64 volts there. And it's, of course, it only needs 39 for doing all the drops, so I don't know, you can calculate the numbers, but I might just do some thermal tests on that to see if it works at 700 milliamps. These LEDs could be underrated, of course. So yeah, I might just leave that running for a bit, do some thermal tests. I won't bore you with this video for doing thermal tests and things like that, but if I find it's adequate, and it's outside, you know, so it'll get some airflow and stuff like that. So I'll just leave it like that's not getting too hot. I mean, I can keep my hand on that, no problem. So 7 milliamps constant current, 40 volts. I think I've found a winner, chicken dinner. I'm going to repurpose these lights. All I've got to do is figure out a way to mount this round thing on the square beam at the top. I don't know, I might make up a couple of little brackets, angle brackets or something like that. Yeah, anyway, yeah, I won't bore you with the details, but there you go. Hope you liked that video where I'm replacing these crusty old strips, and as it turns out, yeah, quite a few of these actually shorted out. If you know the exact mechanism why, I believe I wasn't overdriving them. 700 milliamps I think was like half of their maximum drive current, I believe. I think the CREE XPGs, I have to double, here's the data sheet anyway, for the CREE XPG LEDs, and I don't think I was running them particularly hard at all, but yeah, they lasted like 7-8 years outside before they started to die, and then one went, and then, you know, a couple of, I think we only had like 2 or 3 per strip, as you saw, however many were shorted there. And yeah, they just went short, which is good, but they are finally just one of them in each string went open and they just didn't work anymore. So yeah, had to replace it, and it looks like I might just get, it's getting a bit warm-ski now, but we don't use our outdoor lights all that much. But anyway, yeah, more thermal tests required outside the scope of this video. But anyway, I hope you liked that. If you did, please give it a big thumbs up. As always, discuss it down below and check me out on all my alternative channels. And as I said, I'll put a link to that very cool Mixig current probe. It's a brand new design they've just released, and it really is quite funky if you're after a really, you know, top quality current probe for your oscilloscope. Catch you next time.